So page 10, question 1. Define gravitational potential. Okay, this one is supposed to memorize. Work done in bringing unit mass from infinity to the point. Okay. Part B. Explain why values of gravitational potential near to an isolated mass are all negative. Okay, so that means why we have to put a negative sign to our formula. Okay, so the easiest reason is you can say is attractive. So forces are always attractive. This is the easiest point where most people can think of. Negative because it's attracting, so negative. So the next 2 points, maybe you can think of it or maybe no. So you have to memorize it. So first you say potential at infinity is defined as 0. As 0. Then next point you say, so work got out. Work got out means work is negative. Okay, in moving to the point. So you want to move an object, an isolated object, from infinity to a particular point which is nearer to the Earth, let's say. So it is going to become more and more negative. More and more negative. Okay. So because of that, work got out. Work got out means work is negative. So you see how we take it. Work equal to force time displacement. Force time displacement. So your force is negative. Then your work done is negative. Your force is negative because it's attracting, right? Attracting, then negative. Then end up with your W is also negative. So that means when W is negative, you just say work got out. So it's negative. Okay. Now let's see the next part. Part C. Part C. The Earth may be assumed to be an isolated sphere of radius 6.4 times 10 to the power of 3 km with its mass of 6.0 times 10 to the power of 24 kg, concentrated at its center. An object is projected vertically from the surface of the Earth so that it reaches an altitude of 1.3 times 10 to the power of 4 kilometer. So calculate for this object the change in gravitational potential. Okay, so change in gravitational potential, the formula is change in gravitational potential is equal to final phi minus initial phi. So which is minus g m over R final minus negative GM over R initial. This is the gravitational potential formula. So we just factorize it first. Okay, so we factorize out the GM so that it becomes 1 minus 1 over R final plus 1 over R initial. Okay, now we substitute the G 6.67 times 10 to the power of negative 11. The M, okay, so I changed my mind. The working is very long, so I don't want to write here, not enough space to fill in the value. Okay, now let's say I do it here. The G is 6.67 times 10 to the power of minus 11. The M is 6.0, 10 to the power of 24. The R final and R initial, you take it like this. So imagine this is the Earth. This is the Earth. You are launching an object. Let's say a rocket again. You are launching a rocket. So initially the rocket is on the surface of the Earth. So you can assume this is the radius of the Earth. Okay. So after that, the rocket is launched to a place which is having an altitude of 1.3 times 10 to the power of 4. So we have to know that here to here is the R final, is the radius of the Earth plus the altitude. Okay, so where the altitude is just here to here only. The altitude is just that part. So we have to include the radius of the Earth as well. Okay, so that's why minus 1 over the final is the radius of the Earth. Radius of the Earth is, they give km. Our SI unit is meter. Okay, so 6.4 times 10 power 3 times 10 power 3 again, change to meter. Then altitude also change to meter. 1.3 times 10 power 4 times 10 power 3. This is R final plus 1 over R initial. 6.4 times 10 power 3 times 10 power 3. Then we press calculator for everything here. Then we will get 4.19 times 10 power 7 joule per kg. That's the answer. That is the change in gravitational potential. Okay, so now this side. The speed of projections from the Earth surface, that means this is the escape velocity, assuming air resistance is negligible. Okay, so just now we already discussed how to find out the escape velocity, but you have to be careful. Just now during our discussions in the note, we use the concept where the final energy, if you still remember, just now we our discussion is something like this. I write down first the initial kinetic energy plus GPE initial equal to KE final plus GPE final. Okay, so and just now, right, during our discussion, we said the KE final is 0 because the object reached the destination and stop. It's 0. Okay, now we can still remain using that. It's still 0. And just now, when we do discussion in the note, we say that the rocket go to a place which is very far away with r equal to infinity. So at that time, the GPE final is also 0 because r is how come I write GME? Because r is in infinity, so the GPE is 0. That is during our discussion, but now you must be careful. The object is not launched to infinity, The object is launched to a place which is not too far away, just 1.3 times 10 to the power of 4 only, not too far away. It is not infinity. So we can't assume that to be 0. This is not 0. So remember that. Our GPE final is not 0. It's not 0. So you can't use the concept in the note just now and assume that it's 0. So we just assume that there is a value. There is a value. Minus G M M R final. Okay. Be aware of the formula also. Gravitational potential is minus Gm over R. Gravitational potential energy is Gmm over R. So that is another M there. Okay, so be aware of that. And now, GPE initial is minus Gmm over R initial. Initial kinetic energy 1 over 2 mu square. So we are looking for U. We are looking for U. The thing here is we can cut away all the M, We can cut away all the M. The small letter M. We can cut away. Okay, because it exists in the equation. So we can cut away the M. And then we have 1 over 2 U square. And if you're aware of that, after you cut away the M, the small m, the GPE just now become gravitational potential already. And we just count the gravitational potential as this value, 4.19 times 10 to the power of 7. So, which is something like this, which is minus GM R final plus GM R initial. If I shift the GPE initial to the right, and of course I cut the M already, so these two on the right is actually the gravitational potential, the change in gravitational potential, where you can see I do final minus initial just now, and that value is 4.19 times 10 to the power of 7. Okay, so I already count this. So we times 2 and square root, and then we will get the value. This is the escape velocity or the speed of projection, 9150 meter per second. Okay, so be careful. Try to know how to derive the formula so that when the situation change, you still know, you're still able to work accordingly. Okay, now D. So that's why the equation v square equal to u square plus 2as is not appropriate for the calculation in C part 2. In C part 2, we use conservation of energy to count. So we need to know why this formula is not suitable. This is the formula in the linear motion, the Stewart formula. So all those formula, right, we must remember the basic concept is the A is a constant. The A is a constant, but here it is not. A is not constant. You know, okay, maybe I just write down first. Acceleration is not constant. Okay, acceleration is constant when it is around the surface of the earth, where for free fall or for vertical motions, acceleration is constant and take the value of 9.81. But this is all the way to the outer space. So only Earth's surface can have a fixed value of gravitational acceleration. So when they reach outer space, it is not that value anymore. So it changed to something else. So it is not constant. So we can't use this.